so these kind of terminologies that are being used, cyclonic system has formed, and now I hope that you are clear on what is the cyclonic system that we are talking about. It's either the low pressure system or the wind, the anti-clockwise motion of wind. Anticyclone is a high pressure system, which is the clockwise motion of wind. A low pressure system is a cyclonic system, but it's a well-defined region, like that circulation that is well defined, which is seen on maps. Okay, and then you have this well-marked low, which is again when the low pressure intensifies further, then it's a well-marked low, and then it's depression, and then finally into a cyclone. And then there are two other things that we have not touched upon, but we will do it when we talk about monsoon, which is offshore trough. It's very important for west coast of India. What is that? How to find that, and how to find those on maps? That is something that we will see. And monsoon trough and monsoon circulation. So when we talk about monsoon, we will have a clear idea on the last two things. So this I have already covered. I'm just going to skip because I think I already showed what is a low pressure, what the winds are, and what is high pressure, how the winds move in a high pressure. And low level convergence, high level, upper level divergence is the recipe that actually gives rise to a lot of intense cloud formation. Correct. So you're always on the lookout for for the low level convergence or low pressure on the surface and upper level divergence. That is the recipe for inclement weather, and this is the recipe for a clear sky. So convergence. Yeah, so that is what is needed for a clear sky. Okay. So this is some movie that I do it in my lab. Yeah, so this is a movie which actually shows convergence and divergence. Okay, so these are things that we can show it to the students and show them how things converge and how things diverge. So low pressure and high pressure systems, we can actually demonstrate in the lab as well. So just a short movie that is a part of the curriculum at IIT Bombay for the students to appreciate these weather dynamics. So this is the chart how to find low pressure on on the synoptic scale pressure charts, and also on when you see the wind charts. Okay, trough and ridges also we have covered. How a trough helps? Again, it helps in updraft of moisture, leading to formation of clouds. So not something that we need to go into detail. So now let us look at a semi-complete picture as to we have talked about these different levels, right? We talked about surface, then we talked about 800 HPA, then we talked about 500 HPA, then 300 HPA. So now putting all these things together, if I'm a meteorologist or I'm a forecaster, what do I look for? So at the surface, I look for this low pressure, which is the low pressure system that has formed. So I look for that. And if you remember my second or third slide, where I had drawn a schematic, I told you that whenever there's a low pressure, it will be surrounded by high pressures on both the sides. So that is exactly what is happening. You see, there is a low pressure and it will always be surrounded by a high pressure. Okay. And then at 850 millibar level, I'm looking for these fronts, which are the cold front and the warm front. So this is a cold air moving in, this is warm air moving in. Why is merging of cold and warm air important? Because when cold and warm air meet, they exchange the moisture and they lead to formation of clouds. So let me give you a scenario where there is only warm air. Okay, the warm air keeps moving up, and it will move all the way up to, let us say, 10 kilometers. Okay, so it will form, if there is only warm air, it will only result in it will form clouds which are at a very high level, which are at 10 kilometers. The base of the cloud is at 10 kilometers because a warm partial condensation happens. For the warm air to condense, it needs that much amount of height to become cloud. And 10-kilometer level clouds are called cirrus clouds, which don't give any rain. Okay, they are seen as wisps in the sky. They just look like streak lines. They don't give any rain. Okay, So for the air to condense faster, you need to mix dry air and moist air. Okay, that is when they will mix together and they will start formation of clouds at a very low level, which is at 700 millibar level, which is 3 kilometers from the ground. And those clouds are the ones which actually give rain to us. Okay, so that is why the frontal, so the mix, the uh, convergence of this cold air and warm air is very important. And that's why the fronts are very important, because the fronts is what actually result in formation of low level clouds. Okay, and I look at this trough pattern because this trough is going to ensure that it's going to deposit vorticity. Okay, and it's going to ensure that the clouds are going to become taller and taller and taller, because tall clouds have tendency to give rain for longer period of time. Okay, and finally they will reach the upper level, which is upper level divergence, which will ensure that as the air is getting evacuated, air from bottom will keep moving out. So it is like an engine where whatever comes out, something from the bottom goes in, so that this engine will keep running. So it is like a, so every time you need to start the engine, but once you start, then the engine keeps running, right? So this is like that. So in terms of analogy, whatever happens here is like an engine which gets kick-started and it gets sustained unless one of them breaks down. So either the low pressure breaks down or the upper level divergence breaks down, because if the upper level divergence breaks down, then there is nothing which is go. So because now they will assume that upper level divergence is not there, then there is, it's like a wall. So that wall will just keep, this air will keep hitting and moving down. So it will not, it will, at some point of time, the system will decay. Okay, so unless all these three things are active, which is the low level formation of front, 500 millibar level vorticity deposition or advection, which will ensure that the clouds keep forming, tall clouds keep forming, and upper level divergence. So this is the engine that drives any system. So until the time this engine is active, your system will keep depositing. So it will keep giving rains for a period of 2 days, 3 days, 4 days, or even 10 days, like what happened with cyclone Burevi, where almost for 8 days consistent rains were there for coastal Tamil Nadu. Okay, so only when one of these things break down, then only the system will decay out. Okay, so this is the picture that every meteorologist wants to see from the weather charts. Okay, this is what I am looking for. This region, this particular region is what I am looking for.
Sir,
Yes.
sir, in the chart, actually, what you showed now, sir, that low pressure. So you have showed low pressure now, sir. Is it at 850 MB?
No,
Is it
so low
850 MB?
pressure. This is
Or at,
surface. This is surface low, but the signature of that surface low will be seen at 850 millibar also, because whenever a low pressure forms, the signature will always be visible at 850 millibar also.
okay, sir. At 500, can you please explain? Is it's looking similar to 250, sir? 500 for me. Can you please explain? I can't understand the difference
So
between 500 and 250, sir.
So 500 millibar level is different from 250, because at 500 millibar you actually look for the instability which we talked about. So which is the trigger for vorticity deposition. So the dipping down, or the trough pattern at 500 millibar actually indicates that there is a lot of vorticity deposition, and that is going to actually help the clouds to sustain. Okay, whereas this this particular thing at 250 millibar means that at 250 millibar the winds go and they just move out into the free atmosphere, because that is where the troposphere ends. 250 millibar is where the troposphere kind of ends. Okay, so whatever you are seeing here is vorticity, but whatever you're seeing here is a divergence. So divergence means now the winds come and they just move out. Is it clear
But
what I
both shapes are almost same, sir.
Don't
But
look
the
at the shape. Don't look at the shape. This is what I'm saying. The shape may be similar, but their mechanism is different, or what they are bringing to the table is different.
so at the 250, it's just diverging. But at 500, can you please?
At 500, it is actually depositing vorticity. It is aiding in the deposition of vorticity. That means at this level, whatever has been advected, so whatever air parcel is moving up, it will keep moving up.
Okay, sir.
At this
So
level, it will start getting out.
so at 500, how can we tell whether the vorticity advection is there or not, sir?
by this trough formation, trough. So I think I'll go to this one, which had a better, this one. So trough, when there is a dipping pattern, then that kind of means that there is going to be deposition of vorticity. So the dipping lines. So this region is probably a high deposition of vorticity. This region is low deposition. That means this is not going to help in formation of clouds.
So the dipping of the pressure lines are important. Okay,
Yeah,
sir.
dipping of pressure or vorticity lines are important. Okay. So the hierarchy. So we listen different terms: trough, low, Wilmar low, depression, deep depression. What is the difference? The difference is not much. The difference is that as you keep going into these in this direction, the pressure decreases more, winds increases more, and there is more moisture convergence. So a trough will have compared to a deep depression, the trough will have a relatively higher pressure and low moisture convergence, but still it can give rains. But a deep depression will give very heavy rains for a longer period of time. Okay, and the only difference is in the ease of formation. Or trough can easily form because these undulating patterns of wind can easily form. Whereas to form these closed loop structures, you need you need a lot of conditions to come together. That's why you don't see cyclones forming every day, because you need like 5 or 6 things to come together at the same time and in the same magnitude. Then only you can actually get to a cyclone status, correct? So the ease of formation is the trough is very easy to form. Deep depression is not that easy to form. Okay, so that is the difference. Everything, all of them actually are rain-bearing systems. The only difference is in their anatomy and in the ease of formation. All right. So this is the wrap up. Like, what are the parameters that govern weather? And if you are a weather enthusiast, you should look at pressure, wind, temperature, moisture. You forget, because wind will tell you whether moisture is coming in or going out. Because if the winds are coming from sea to land, then that means there is a lot of moisture. So pressure, wind, and temperature. These three things, if I am able to look, then I can actually get a good handle on weather dynamics. Okay. All right, so this is one of the important aspects, I think, which was also discussed. Why is Arabian Sea heating up? Is it because of climate change? So I'm going to try to explain it using this radiation balance, which is solar insolation, right? So there was one basic element which I called solar insolation. So the amount of sun's energy coming into atmosphere, okay, how does it get balanced? Okay, so what is the role of Earth and atmosphere in this radiation? So just remember this equation. I will tell you the terms in these equations at the end. Okay, but just remember this: R net minus G equal to H plus LE. This is the radiation balance for the Earth. Okay, don't worry about the terms right now. I will tell you. Just hold on for five or 7 more minutes. Okay, so this is a complete picture. Let us break it down. So solar forcing. So amount of energy from the sun is coming in as a short wave. Okay, and as it comes, 70% of that is absorbed by the Earth, and 30% is reflected back, which is the albedo. 30% is the average albedo, given an year that can change. So some years it is 50, some years it could be 10, but average is what I'm talking about. Okay, so right, so this is where one of the questions was asked, like albedo changed and that led to a deficit monsoon. Yes, that happens, but that is the seasonal variation. I am talking about average. On an average, 70% is absorbed by Earth and 30 is reflected back. And out of that 70 that is being absorbed, ground takes up 51%. So this is just a number. Okay, so I'm just giving an example. I'm not putting exact values. So assume that 100 units of sun's radiation are coming onto Earth. Out of that 100 units, 70 units are being absorbed. 30 units just goes back into the space. Out of that 70 unit that is absorbed, 51 is taken up by the ground, 17 is taken up by the gases and dust in the atmosphere, and 2% by the cloud cover. Okay, so that makes a total of 70. 30 is reflected back. We don't care about that because that is not going to play any role in heating of the Earth. Okay, so just look at these numbers. So out of 70, 51 is taken by the ground, 19 is taken up by the gases and clouds. All right. So now the question is, we are getting a lot of radiation. So then why are we not boiling, right? So the answer is that the ground receives the solar radiation from the sun, and it gives back long wave radiation. So that short wave and long wave, it can be realized by the fact that there is this equation which says lambda max, which is the wavelength of radiation, T is the temperature. Since sun's temperature is equal to a constant B, since sun's temperature is 5000 Kelvin, this lambda max should be smaller. So that's why it is short wave. So whatever comes in is short wave. But once the solar radiation comes to the earth, the temperature of the earth is around 30-35 degrees. So to have the same constant, this lambda max should be large. So temperature reduces, lambda increases. That's why it is a long wave radiation. Okay. So whatever comes from the sun is short wave. Whatever is emitted by the ground is long wave. So the reason we are not boiling is because whatever is received by the sun is converted into long wave and sent back into the atmosphere. Okay. So what is that thing that is being sent out to the atmosphere? So 51 short wave is received, 19 is short wave is received by the atmosphere. Now this 117 is the long wave radiation that is being lost by the atmosphere. Sorry, lost by the surface. Okay. So this 117 is the long wave radiation that is emitted from the surface to the atmosphere. So out of this 111, 117, 111 is taken up by the atmosphere, and 6 units is taken up by the is directly sent to the space. So let us not worry about that 6. We will only worry about the 111. Now the important thing to remember is that 111 actually becomes 160. Why is that? Can anyone, does anyone have a clue? So the scenario so far I will explain. The scenario so far is that the shortwave radiation is 51 that is being received by the ground. That 51 becomes 117 because of the shortwave to long wave change. Okay. So as the shortwave radiation hits the earth, because it is getting converted into long wave infrared radiation, it enhances its energy. So that long wave radiation is now sent back to the atmosphere, and that atmosphere takes 111 and 6 is sent to the space, which we don't care about. But that 111 becomes 160. The reason is because of the chemical reaction due to the greenhouse gases. So we have greenhouse gases, and this is where the greenhouse gases play a very, very important role, because they take the energy and they excite it. So go back to your chemistry days. You know that from chemistry we have reactions, right? All these chemicals. So what is gases? Gases are nothing but chemical compounds, correct? So those chemical compounds can actually interact and they can enhance the energy. So they can elevate their energy state from one to the other. So the NOx, the SOx, the NOx, the SOx, which is sulfur, nitrous, carbon dioxide, carbon monoxide, whatever gases, greenhouse gases you want to take, all of these actually act in the atmosphere and they enhance the atmospheric energy, atmospheric state. So now what happens is atmosphere has 160 long wave radiation with it, and it will send 96 back to the earth and 64 back to the space. Okay. So let us not worry about this 64. Let us only worry about this 96 that is coming back to the earth. So although it is a complicated mathematics, but I think it's very straightforward. We are only looking for two things. In the end, we are only looking for two things. We are looking for the amount emitted by the surface and the amount absorbed by the surface. Okay. And we are looking for the amount emitted and absorbed by the surface and atmosphere in two different regions, which is long wave and short wave. Okay, so atmosphere takes the net long wave radiation that atmosphere has is minus 49, because 111 is absorbed, 160 is emitted back, so minus 49. Surface net long wave radiation is 96 minus 117, because 96 is absorbed, 117 is taken away. Okay. Similarly, the short wave part, net deficit in the atmosphere is minus 30. So atmosphere has a deficit radiation. That's why always atmosphere is at a cooler state than surface. Okay. And surface has a surplus of 30. So what happens is atmosphere and surface are in balance. So whatever the deficit is in the atmosphere is surplus in the surface. Okay. So this is the balancing act. So now the surplus that is present in the surface, what happens to that? Where does it go? it goes to land or ocean. Okay, and I will tell you how. Just give me 1 minute. I'll tell you how it goes to land and ocean, and how it actually heats up the land or the ocean. This is how the ocean is warming. The ocean
Sir,
is warming. 1 second, just let me complete. Give me 2 minutes, okay? The ocean is warming because of the greenhouse gases, and this is where I want to bring that question: that is it because of global warming? Yes, it is because of global warming, because the greenhouse gases are the one which are elevating the temperature from 111 to 160. Okay, so that is what is actually the excess heat that is being given, that is gained by the surface, and that surface, Earth's surface, has to give it somewhere. And we all know that the sink is ocean. Ocean is the largest sink. It will take whatever you give. You tell that take away 100 watt per meter square of energy, it will take it. You say take it 200, it will take it. Okay, but it will slowly release it over a period of 10 to 20 years. It will take it. Okay, it will take it, and it will pull it down to the bottom of the ocean or deeper layers of the ocean. But slowly over the decadal cycle, it will slowly release that heat, and that slow release of the heat is what is seen as the um, extreme events that we are seeing now. So whatever we are doing now, we won't see the repercussion of that now. We will see it 10, 20 years down the line, because whatever heat we are generating, excess heat we are generating because of the greenhouse gases, which is what is the key for climate change. So climate change is nothing but heating of the ocean. Okay, that is what in simple terms climate change is. Heating of the ocean is directly related to these anthropogenic activities like greenhouse gases and cutting down of trees, because if the surface has taken 30 units extra, then it can either release it as sensible or latent heat. Latent heat is nothing but the heat that is being released when the material changes from liquid to gas. Okay, so for instance, if you have a lot of lakes, if you have a lot of water bodies, if you have a lot of trees, then the trees will take away the heat through evapotranspiration, like because all the trees have water in them, right? So they will slowly take away these heat. But what we are doing is we are not allowing for this for this excess heat to go as latent heat, because we are creating reclamation land. Our lakes are not restored. We are building on lands which are where the lakes should be present, and we are cutting trees. We are blocking the heat that the trees could have taken, and all of this basically comes back as heating, additional heating. Okay, so let me now explain what is this balance. R net is the amount of heat that is being taken by the surface. Okay, the Earth's surface, what is the amount of heat that is there? G is the ground soil moisture. So whatever heat that is being taken by the surface can go to the soil because the soil is cold. And whatever additional is there after whatever goes to the ground, that is being exchanged between sensible heat, which is the actual heat that you feel. Okay, H is the sensible heat, which is sensible heat is nothing but the actual heat that you feel. Le is the latent heat, which is the heat that goes as moisture. Okay, so if you are going to reduce the amount of lakes that are present, then you are going to increase the H, and that is exactly what we see as our body. Our body what feels, because our body directly feels H. Our body doesn't feel Le. Our body directly feels the sensible heat. So if you cut down the sources of G, so if you let's say there is no soil moisture, there are no lakes, then whatever heat is present, you will directly feel it, and that's why you are seeing temperatures which are reaching 40 degrees, 45 degrees. Some places in Rajasthan seeing 50 degrees, right? I mean, it's getting crazy, because we are blocking every avenue of heat that can be seeped out. The only avenue that we have left out is ocean. Okay, and that is exactly where so energy from thermodynamics first law, you all know that energy can neither be destroyed nor be created. It can only move from one form to the other. So the form it is moving is from land, it is moving to ocean. And ocean, it takes in a lot of heat and it will slowly release it. Ocean has this behavior where it will slowly release the heat over a period of 10, 15 years to the surface. Because of a lot of these deep layer ocean dynamics that we call, it will slowly release the heat. And that is exactly what is happening, and that is one of the reasons why Arabian Sea, which was not warm 20 years back, you can see the records. You can see the Arabian Sea temperature records 20 years back, and you can compare it with today. It has warmed definitely by I don't know. I mean, 2 to 3 degrees at least. I could convincingly say, and that is mainly because we have cut down avenues of soil. We are concretizing everything. We are putting a lot of urban heat islands. We are cutting down lakes. We are cutting down trees. We are not allowing for the heat to seep anywhere except to the ocean. Okay, so that's the simple explanation for the increase in extreme events and extreme rains, because ocean heats up means ocean will provide more energy to the atmosphere, and more energy means more moisture. More moisture means more intense cloud formation and intense rain events. Okay, so I just wanted to complete this. Now I think somebody had a question. You can ask me.
Sir, can you please show that 30% that how that 30% is coming, sir? You told net absorbed by the ground is excess 30% and emitted by the clouds is yes,
That is
this one.
that is coming from balance. So if you what I would suggest is you when I share the slide, you take a look at it, because it's simple math. It's just difference between the emitted and absorbed. So whatever is emitted, whatever is absorbed, if you subtract that out, you will get the 30.
Okay, sir.
So let us not worry about. I mean, I am 100% sure this is right. So because I don't want to spend time explaining that. What I'm saying is 30 is the right number. Um, I mean, 30 right number in the sense, hypothetically speaking, this 30 could be 70, 80, whatever. I don't know. I'm just telling you that whatever extra energy that is gained by the surface, that has to go somewhere. And if we are closing all the avenues of natural avenues like trees, soil, then this additional energy is going to go to the ocean. Okay.
So, Professor Sridhar,
Yes.
I have a question. Can you comment on global phenomena such as La Nina, El Nino, those things? Because for example, this year is supposedly a La Nina year. Is climate change causing the La Nina years to be shorter? The phases of La Nina, the duty cycle between, I mean, what we in engineering would call this as duty cycles between La Nina and El Nino. El Nino years tend to be, I mean, El Nino period tend to be longer when compared with La Nina. What is the effect that this is having on for us?
Yeah, that's the question that I think the clear answer doesn't exist. But yeah, you are right. The duty cycle of these El Nino, La Nina events are changing. One thing is that if you look at the historical records, then El Nino used to occur every 5 to 7 years. But now we are seeing more El Nino. I mean, more events of El Nino as such. The duration of the El Nino is something which is what we call as the intra-seasonal phenomenon, which is not so. If I look at it from a purely scientific viewpoint, then El Nino actually has a growing phase, it has an onset, growing, and mature phase. Okay, and if you keep aside climate change, then you can actually pinpoint these three phases: the growing onset phase, growing phase, mature phase, as a cycle, which is the onset starts somewhere close to June, July. Then it kind of develops. It matures in February or March, like in that year. Okay, that is what the climate scientists have said. But now you put this additional thing, which is climate change, and the things are getting too difficult to kind of predict as to what happens. Okay, and I'm not able to comment on what is so I'm not able to comment on. Statistically, I can comment, but dynamically, I'm not able to comment on what is the role of climate change on El Nino and La Nina, because it's not well understood.
Okay, one more question regarding the coupling of atmosphere and ocean. For example, this year is supposedly a La Nina year.
Right.
Generally, La Nina years are not good northeast monsoon years. That's what we would predict. I mean, based on previous data and experience. But this year we had a bounty for because our Chennai lakes are 90% full. This is what I always look for. Okay, Chennai lakes are 90% full. Next summer, no water problem. The reason is that it is attributed by other enthusiasts, weather bloggers, my friends. The reason they attribute is because there has been not a good coupling between the ocean and the atmosphere. In the La Nina state has not yet reached the atmosphere. So we got what we got because of this. I mean, what is happening?
So whenever the WMO, which is the World Meteorological Agency, or any body like NOAA, when they announce La Nina, that means that the atmosphere and ocean have coupled. So unless and until it has coupled, they will not announce the actual occurrence of La Nina or El Nino. Okay. So there is I have no doubt that the atmosphere and ocean have coupled, because it is seen in the form of course, the heating and cooling of the Pacific, plus the Walker circulation cell that I will discuss later, that ascending branch and descending branches, which are actually seen in terms of, so there are pressure stations in Australia and Chile, and if you look at the ascending and descending limb of these Walker circulation at these two locations, you can actually see that the ocean and atmosphere have coupled with each other. Okay. So your question is very valid, that La Nina, so that this is what I also thought, that La Nina is not good for northeast monsoon, but I'm not very sure what happened this year. I think it is something which we need to look back. But one of the things is that slowly climate scientists are believing that El Nino and La Nina are not the only state which govern the Indian summer monsoon, both summer and winter monsoon, which is both southwest and northeast monsoon, because our new friend, which is the Indian Ocean dipole, okay, that has kind of come. And if you look at last 2 years, 2019 and 2020, 2019 was kind of a developing El Nino year, because if you see although ocean and atmosphere didn't couple, but it was kind of a pseudo El Nino, but we got 110% excess thanks to the positive IOD which developed.
Yes.
And this year, if you look at the northeast monsoon, La Nina year, but you are right, it is 8% or almost 9% excess. So I think all the climate scientists are in kind of conjunction, or they are in consensus that the Indian Ocean dipole is slowly becoming more driver of our Indian monsoon season than El Nino and La Nina. And these Indian Ocean, since Indian Ocean basin is smaller, the changes in Indian Ocean happens on a quicker scale, and that needs to be looked into.
Okay, thank you.
I agree with that, because Indian Ocean dipole is something which not much research has been done. It was introduced in 1997, whereas La Nina was introduced in 1915. So we know a lot about La Nina and El Nino, but even after that, we cannot. So I cannot predict whether in 2050 year will be a La Nina, because what we are doing is we are looking at La Nina and El Nino from observation. We are looking at only the evolution of sea surface temperature, and then we are kind of retrofittingly saying that La Nina has evolved, but we are not able to predict whether 2030 will be a La Nina year or so. So the same thing is happening with Indian Ocean dipole, in the sense that we are kind of looking for this indices on a get-go basis, like for the next 15 days, how it is behaving. So that is not able to gel well with our long-term predictions, as in whether next year summer monsoon is going to be excess, next year northeast monsoon is going to be excess. Our long-term things are very poor. So these we are still at a state in weather prediction where we are still using a lot of these in situ kind of data, which is just allowing us to say something which can happen only 4 or 5 days ahead of time.
Thank you.
So one of the things is that we always talk about is why are we not able to predict La Nina and El Nino events, although we know so much about them. Like we know how they form, what is the mechanism, everything, but we are still not able to, because there is one thing that we still don't understand clearly, is the thermocline. I will talk about that later. It's too technical, but if needed, we can talk about it tomorrow.
Okay. Sir, just to add.
Yes.
Other than the Indian Ocean dipole, I think even the Madden-Julian oscillation also plays an important role, right?
See, Madden-Julian oscillation is again your intra-seasonal variability, but it is in atmosphere. It is again connected to the ocean. So MJO prediction is also very dicey because it depends on the state of the ocean again. So what every time people miss out is the role of the ocean in prediction, and we only look at atmospheric phenomenon too much. We don't give the respect that the ocean deserves, because MJO is again air sea coupling. Unless and until your ocean is going to give the heat, MJO will not come to our basin. So role of ocean is very, very important, which we are unable to embrace, or which we are unable to predict because of a lot of things. Ocean is one of the most difficult things to predict. I'll tell you why when we talk about GCMs. So MJO is there, but MJO is actually linked to your ocean, and MJO is not something that. Let me put it this way. El Nino and La Nina are the synoptic scale phenomena that have a more bearing on monsoon, and MJO is just a driver of the monsoon, in the sense that MJO will just tell you whether the rainfall is going to get switched on or switched off. It's not going to govern your monsoon as such, if I may say that.
Thank you, sir.
Yeah, the three or four things that govern the monsoon are the ocean circulation, which is this El Nino, La Nina, or IOD, or even the Atlantic modes. Yeah, Atlantic also has a Nina, Atlantic Nino. The Nino is present in these, plus the wave action, the Rossby waves, Kelvin waves that we will talk about later. So MJO is just one of these phenomenon that, but I don't have a feeling that it is actually governing the monsoon. It is just making the monsoon break and active phase. So, but it as such it doesn't govern the evolution of a monsoon. That's my feeling. I may be wrong.
Sir.
Yeah.
Sir, due to less pollution, does the monsoon is it good? Sir, due to the less pollution this year, has northeast monsoon performed very well, sir?
I don't know that. I don't know that because. Yeah, I don't know that because I mean I don't want to comment because it's not very clear yet. Why it would happen is not very clear yet.
Because we had 2 summer rains also, sir. In Chennai, summer rains are very rare, but due to lockdown, I don't know, sir. I have doubt in that, sir. Is it due to that low pollution?
Yeah, I don't know the mechanics why it would happen. That's why I'm not ready to comment on it. Like I don't know the mechanics of it. So
I have 2 questions about the ENSO. Will this be an appropriate time to ask, or somewhere later during the course?
Yeah, we have an ENSO module later. So yeah,
okay.
It's there. So we will talk about ENSO and IOD in detail.
Okay, thank you.
Okay, so front side. So yeah, so I think since cloud formation condensation everybody knows, so I'm just going to skip this. And so just the important aspect here is 2 important modes of formation of clouds is through this front, which is the cold front and warm front interaction. I will talk about these fronts in detail when we take up the processes part, or the orographic lifting, where is the rain shadow region is what we call. So so on the lee side of on the windward side it will form, and then on the lee side it will form, and on the windward side it will drop. So the orographic lifting is the other way of cloud formation. Different types of clouds. I think this I can skip. You can take a look at it when you have time. But important clouds that we look for is the nimbostratus, stratocumulus stratus, and cumulonimbus. These are the 4 important clouds which are the rain-bearing clouds. This is something that we do here to demonstrate cloud formation. We take a candle holder, 2 candles. One of them I fill it with water, other has no water. Just to show that you don't need boiling water for formation of vapor, because this is not steam, this is vapor. So vapor can form even during convection. So there is convection. Because of convection, the air parcel rises up and it condenses into clouds. So this is a simple experiment to demonstrate cloud formation. You can do it at home to show your kids how clouds form. Not a very costly setup. It takes. I mean, you can build it at home. Rain, of course, ultimately all we talk about is rain. So rain occurs because of the water cycle, whereas there is evapotranspiration, condensation, precipitation, and runoff. So I'll not talk about that too much. So I want to spend the next few minutes. So we will come back to the instruments later. I just had this because I thought we can talk about instruments, but maybe we don't. We can talk about it later. I want to spend the next few minutes, maybe the next half an hour before we break for lunch, talking about weather forecasting, because that is something that I feel. So everybody feels like this model. I mean, I keep getting questions like, how good are these models, and what is happening in these models? Why are they not able to predict? Okay, so I thought I will talk about that a little bit, and also introduce to you what these models do. And what these models are good for, and what you should be doing with them. Okay, so this is what brings us to this weather forecasting, how it is done, and why it is important. Okay. Of course, we do it using models. Okay, and of course, with the models we add this knowledge of dynamics which we have learned so far. Pressure charts, wind chart, how the pressure behaves, how the wind behaves, temperature of the ocean behavior. Adding those dynamics actually gives us a pretty good viewpoint. Okay, and looking at precipitation charts is mostly from statistical viewpoint, because we look at past 100 years of history, and then we see, oh, this area used to get a lot of rain. Like for instance, Cherrapunji, it will keep getting rains. So we make hotspots of regions which are rain shadow, or which are the rainiest places, and all these things. That is how. So these are the three modules of weather forecasting. Early time weather prediction, we'll skip. In absence of technology, people used to look for natural signs of drying of leaves, opening of pine cones, because opening of pine cones means it's wet, dry weather. Closing of pine cones means it's wet weather. But these days we don't have much of trees to give us signals, so we'll not go there. We are more sophisticated now. We have science and technology at our hand. This is the only mathematical slide that I have. I just wanted to throw this at you because I wanted to show you the types of equations that are solved in the weather models. Okay, so you have mass, then you have the momentum equation, you have the energy equation, you have the salinity, which is for ocean, you have the moisture, which is for atmosphere, and you have this equation of state, which is for pressure. Okay, so total you have 7 equations for atmosphere, you have 7 equations for ocean, and you have the radiation budget for atmosphere. Sorry, land. Okay, because amount of energy that is being received by the surface, that is playing a very important role, like I already told you, because that is what is going to govern how much heat is present for heating the parcel. So 15 equations are there, and 15 equations are solved by something known as weather or climate models, or something known as earth system models. The difference between a climate model and the earth system model is that the earth system model solves the same equations, but in addition, it also solves for the chemistry and biology of the ocean, chemistry of the atmosphere and biology of the ocean. So what do I mean by chemistry of the atmosphere? Earth system models actually solve for the reactions between the greenhouse gases. So how the elevated state of atmosphere is received. So Earth system models are the much realistic model, because they solve for everything that you have, all the processes that are there. But weather and climate models, they don't solve. They don't care about the chemistry and biology. That's why weather and climate models have some deficiency, because it is not a complete representation. Okay, but nevertheless, weather and climate models are the ones which we use, because we can run them on a faster time scale, whereas Earth system models will take very long time. And for prediction purposes of weather and climate, this model is used, weather and climate model, because we need everyday prediction. Like we need to know what is going to happen tomorrow, what is going to happen in next 6 hours. Earth system models are so complex that they will not be able to give us daily data. It can only give us monthly data, or maybe even yearly data. All right, so weather versus climate, just one slide I have. Weather is, what is the difference? Because many people mix it. So weather is something that we feel, whereas climate is something that we perceive. Because climate is more like a centurial or decadal scale. So what is going to happen in the next 10, 15 years, how the climate is going to change. And when we talk about weather, we only focus on atmosphere. And this is where I was saying that the importance of ocean is lost because we only talk about what is happening in atmosphere. What are the wind motions in the atmosphere? We don't talk about ocean that much. But when it comes to climate, the importance of ocean is very important because we need to see how the ocean is slowly releasing the heat, okay, and how that heat is how the heat is coming to the surface, because that is what is going to change the climate. Okay, so right now we are seeing more cyclones in Arabian Sea as well. That is a result of climate change because slowly the ocean has released its heat and it has changed the state of the Arabian Sea. So when you talk about climate, you have to look at the ocean dynamic. You have to look at the ocean part very carefully because without that, we cannot see how the climate is going to change in the next 50 years. Okay, sea ice is also important because how the glaciers are melting, how the Antarctic, Arctic pole regions are melting. That is also important for climate change. Okay, so climate focuses mainly on long-term changes of ocean circulation, sea level rise, and ocean warming, whereas weather is only we are talking about atmosphere. Sorry. Yeah, I think so. There was a problem. There was a connection issue. So yeah, okay. Can you hear me now again? Sorry. Hello?
Yes, sir, we can hear you, sir.
Hello. Okay. Okay, so I was so what I'm trying to say get. So why do we call it a climate model? Because the climate model and weather model have the same framework. The only difference is that for climate model, so if you run it for longer period of time and you look for what is happening in a long range, so let's say 1 month, 2 months, 3 months, then it is a climate kind of a scenario. And you can also run the same model for 7 days or 10 days. That is going to give us the weather. Okay, so the framework is the same when you take climate or weather model, but when you take the Earth system model, the framework is very different because it also allows for ocean biochemistry, land CO2 changes and everything. Okay, plant ecology and everything. That is the Earth system model. So for this course, we will only look at climate model. So the climate models have three components: atmosphere, ocean, and land. And out of that, in that, it has a atmospheric ocean component which exchanges information with the atmosphere, and then atmosphere gives the information back to the ocean, and also atmosphere includes land as well, and that is how they interact and they give us the prediction of weather. Okay, that is the basic principle. Earth system model we'll skip for now, not important. So one of the important differences that I already told you is between the weather and climate is two things. One is initial condition versus boundary condition. So your weather model is an initial condition problem, whereas your climate is a boundary condition problem. So what do I mean by initial condition versus boundary condition? So what I mean is initial conditions are the starting point. So for instance, I take a model. Okay, doesn't matter whether it is a GFS model, whether it is ECMWF, whether it is IMD GFS. There are many different models. In order to understand weather, I need to initialize it with initial condition, which is the variables like wind, temperature, pressure, and moisture. I need to force it with this at, let us say, 1 p.m. today. I need to get all these variables. Okay, and how do I get these variables? I get it from observations. I get it from satellite data. I get it from many aircrafts which also give data, radiosondes which give data. Doesn't matter where I populate. I take this entire set of data and I force the model with this, and then I let it evolve for, let us say, 6 hours or 10 hours or 12 hours, whatever it is. That is weather model. It's an initial condition problem. Whereas for climate model, what I need to do is I need to put boundary. So I need to say that between January and let us say March, force the boundary with a solar radiation which is higher or lower, lower, because it's winter for India. Between June, July, and August, force it with some more lower this thing. What is that? Solar radiation because of monsoon. Then comes your summer, which is post monsoon, October, November, force the boundaries with higher solar radiation. Okay, so the difference is that you let the weather model initialize and evolve. There's the seasonal changes that occur in order to understand climate. You have to force that. Okay, so you have to force those the seasonality, which is your winter time temperature or winter time solar radiation reduces. The summertime solar radiation is higher. The monsoon time solar radiation is different. So you have to actually prescribe that on the boundary, and then only you can actually get the climate model to work for a climatic time scale. Okay, that is where the difference lies. Right. Okay, so now if you take so like I said, the GCM solve these equations. 7 plus 7 plus 1 is for land. So 15 different equations it solves. You can't solve it by hand, and you solve it on a grid. So at each grid point, you get a data. You get the data in terms of velocity, temperature, pressure, moisture, and all these things. Okay. So now when you are building this GCM, you need to kind of focus, zoom in on the resolution, or you want to say with what resolution am I going to run this climate model. So there are different resolutions available. So this workhorse model, what I call this workhorse model, is the model which is actually going to give me the evolution of El Nino kind of phenomenon. So I have to run this thing at 1 degree. 1 degree is 100 kilometers. So that means at each 100 kilometers, I'll get a result. Okay. 0.1 means 10 kilometers. So every 10 kilometer, I'll get a data. So the difference is 1 degree will run faster, but you can actually cover a longer time scale. See, there are two things. Time scale and spatial scale are the two important aspects when it comes to weather and climate. You want to cover the events which happen on a period of 1 hour or 1 minute, or a period of 1 week, 1 year, 10 years. At the same time, you want to capture the processes which happen at a spatial scale of 1 meter, 10 meters, 100 meters, or 1,000 kilometers. El Nino are the things that happen at a scale of 1,000 kilometers. Okay, and also happen at a scale of yearly, 10 year, 1 to 10 year is the time scale at which El Nino or La Nina can occur. So you cannot run a high resolution model, because it will not finish, because as you increase the resolution, the time for the model to complete the run will take a longer time. Okay, that's why you have the workhorse model, which you are saying that, okay, I don't want high resolution, because I'm only capturing these bigger El Nino, La Nina kind of processes. So I work with the 1 degree model. There you can try to get El Nino kind of things better. Okay. Then you have one more, which is low resolution, which is 3 degrees, which is for future climate, like what is the climate going to do in 100 years or 50 to 100 years. Okay. Anything which is below this 0.1 degree is what we call weather. These are the weather models, because they actually cover the shorter scale time features. Like these have the capability to resolve clouds. Resolve clouds in the sense, this will tell you how much is it going to rain. These bigger models cannot tell you about cloud physics or anything. These are the models which tell you about the cloud formation, the convection, and all these things. Okay, so there are different resolutions of model, but you choose the resolution that you want. For weather, we take lower resolution, okay, which is 0.1 degree approximately, and then we run the simulation and we get out the outputs. So there are different models: CFS, ECMWF, GFS Icon, and GFS India. Okay, these are the 5 different models that are. There is also UK Met, but I'm not going to talk about that. But these are the 5 different models which are widely used. So what is the difference between each of them? Okay, each of them, the difference is that they have different spatial and temporal resolution, and they have different initialization schemes. Okay, initialization schemes in the sense that the way ECMWF will get initialized will be different than the way GFS will get initialized, because the data that they are going to gather is very different. The way, so ECMWF will get more data. Let's say, for instance, okay, so it has a better network of sensors, so it will get more data to initialize, because I said weather is an initial condition problem. So better your initial condition, better your output. Okay, whereas GFS will have a different type of initial condition, in the sense that it doesn't have a very good network of sensors, so it will have very sparse data, and that was the reason why both of these don't give the convergence. Both the results from ECMWF or GFS will be different. Okay, the way they are being initialized. The second is the spatial resolution. The spatial resolution is also different. Okay. So let's talk about CFS in a little bit of detail. CFS is the widely used climate model. So CFS is a model that has a resolution of 1 degree, 108 kilometers, and it runs for 30 days, or it can also run for more than 30 days. It can even run for 60 days or up to 3 months. So what this does is, this is used mainly for climate forecast. So this is mainly used for monsoon kind of prediction, because you run it for, so let us say today, December, you run your CFS, it will give what is going to happen till March. Okay, so you have an idea whether next year is an El Nino year or a La Nina year, right? Okay, because CFS will be able to tell you. The only issue is that it will not be able to tell you accurately. Okay, so it will tell you that next year's likelihood of developing as a La Nina or El Nino year. Okay, by March, there is a likelihood that El Nino or La Nina will develop. But issue is that we cannot trust this particular thing. The reason is because there are a lot of assumptions. Okay, there are a lot of assumptions, and it has a lot of issues in the sense that it is a boundary condition problem. So how do you know that it has put the January, February, March solar radiation correctly? Okay, how do you know that? Right, we don't know that, because it needs that solar radiation to be inputted to this particular model. Because if it wants to run for 3 months, then the way the January solar radiation changes, the way the February radiation changes, the way the March radiation changes, that has to be put as a boundary condition for this model. That is where things get tricky, because although we are running these climate models, but we don't have any we don't have a lot of trust in them. Okay, because we don't know. I mean, whatever we are putting is scenarios. Okay, whatever we are putting is scenarios, because I'll tell you one thing before we move. The scenarios, where is that? Yeah, the scenarios come from something known as a CMIP projections. So what CMIP is nothing but a coupled model intercomparison project. It was developed by this IPCC assessment report in 2013, and we have different CMIP versions. CMIP 5 is the most recent version which we are using, and in 2021 we are going to come with CMIP 6. So what CMIP does is, CMIP runs 100 distinct climate models. Okay, so CFS is just one of them. ECMWF has its own climate model. UKMet has its own climate model. ICON, Germany has its own climate model. India has a CFS, which is the climate model that it uses. So there are different types of climate models. It does different runs based on the scenarios. Those scenarios come from something known as RCP scenarios, which is nothing but there are different versions. Okay, 2.6, 4.56. Don't worry about the versions. So what the scenario does is, it actually sees the data of temperature over, so whatever observations we have, it takes the temperature change over the atmosphere or ocean, global temperature, average temperature change. And then it kind of extrapolates what is going to happen in the next 100 years. So these are the scenarios. So different scenarios means what will happen if the temperature rises by 4 degrees? What will happen if the temperature rises by 2 degrees? What will happen if the temperature rises only by 1 degree? What happens if the temperature remains constant? Temperature scenario, emission scenario. What happens if the emissions are going to be higher? Greenhouse gas emissions. What happens if emissions are going to be lower? So it puts scenarios. And what about the radiative forcing, which is the forcing from the sun? What happens if the forcing is very high, very low, very moderate, and all these things? So based on these scenarios, it comes up with different runs, and the average of those runs is what is the climate century scenario for the next 100 years. Okay, so this is the scenario that I'm talking about, and that scenario is what is given to this climate forecasting model as the radiative forcing That is why we cannot believe this, because these are all scenarios which we don't know whether they will happen or not. These are like projected scenarios. Okay, so that is why this climate forecasting is not a very, I mean, it's not it's not believable too much. Okay, so that's why we only believe in these weather forecasting, which is a much shorter days. So 10 days, up to 10 days, how the weather behaves, fine. You have some idea. You can actually see how the weather behaves in a shorter time span. Some people say only 5 days is good. Yes, agreed. Only 5 days is good, and there is a reason for that. But nevertheless, up to 10 days, some kind of a scenario can be given, in the sense that in the next 10 days, is there a low pressure which is forming? If the low pressure is forming, where is it forming, and where should we keep an eye on? Okay, that is what these weather models tell us. The ECMWF and GFS model. The difference is in the resolution. Like I said, GFS runs at 27 kilometer, whereas ECMWF runs at 9 kilometers. The forecast days, so it gives forecast for 10 days at a step of every 3 hours, whereas GFS gives much time on a much finer time scale, which is 1 hour. And update also, it updates at every 4 days, where it updates only 2 times per day. So why do we need different GCMs? Why do we need different weather models? The difference is, I mean, the reason is because there are different cloud microphysics and convective parameterization. So all these models have a different emulation of the cloud and precipitation processes. Okay, so ECMWF may show that there is going to be more rain, whereas GFS will say there is going to be less rain. The reason is because the way they have actually built the model physics is very different. Although the equations are the same, the model physics is different, because one will remove more moisture from the ocean, whereas other will remove less moisture from the ocean, and that will show as difference in the rainfall quantum that is being predicted. Okay, so that is one thing. The second thing is convection. How strong the convection is. One model may show a different convection, other model may show a different convection. That is why ECMWF and GFS, they don't converge most of the time. Only in the 2 days or 3 days before the impending event, these two models attain kind of a converging pattern. Otherwise, 10 days before the event, or 10 days, let us say today, you look at both ECMWF and GFS, and you look for December 28th. Both of these will give a very different viewpoint. ECMWF will say there is a low pressure forming in Andaman, whereas GFS will say no, there is no low pressure forming in Andaman. The reason is because the way they are built is very different. Okay, but as you keep initializing these with data, as you keep initializing them with the real data every 6 hours, then they will reach a kind of a convergence. There are different, the icon and UKMet also are there, but again the differences in the equations are the same, but the framework, the way they are built is different. Like the cloud microphysics scheme and the convective scheme that all the models uses are very different. So the last thing before we stop talking about these models is that you have something known as RCMs, which are regional climate model. What is the reason for the regional climate model? Is because the regional climate models runs at a much higher resolution. So regional climate model can run at 3 kilometer resolution. Okay. So when I'm talking about RCM, I'm only talking about atmospheric model. So it only accounts for the atmospheric component of it. So 3 kilometers, what is happening, I can get from RCM, and I can only focus on a small region, let us say India, or let us say Europe, only the small, I don't have to run the globe. But the GCM will give me the inputs, because I need to force this I need to force it with some values on these 4 walls, or these 4 boundaries that I have. So that will come from GCM. Okay, so GCM is needed for RCM. So you can say that RCM is as good as a GCM. That's true. But the good thing about RCM is that it can at least tell us, assuming that the GCM has a very good, a decent prediction of what is going to happen, and if you force it with that, then it can actually tell us whether a thunderstorm is going to occur or not. Okay, so RCM is mostly for thunderstorm type of events, and most of the time it doesn't work very well, because you have a lot of issues, because you are forcing this using the GCM, which also has inherent problems. But weather research forecasting is a regional model, And sometimes it is very useful because sometimes it actually tells where is the high pressure is, where there is a high chance of thunderstorm and where there is no chance of thunderstorms and all these things. So all said and done, the problem is, I think I have kind of given you an idea where the problem lies. The problem lies in the fact that you have limited resolution issue, 27 kilometers, and you have, let us say, between the 27 kilometers, you have buildings, you have mountains, you have small hills, you have small water bodies, and everything is being missed out by these GCMs, which is the global climate models. So the resolution issue is one of the things. The second thing is clouds, which are of the order of, let us say, 1 kilometer wide or even 4 or 5 kilometer wide. They are not able to resolve the clouds. Global models cannot resolve the clouds because clouds are not because the clouds forming within this 27 kilometer, there can be 2 or 3 clouds that can form within this 27 kilometer box. So we have missed out on all these cloud formation mechanisms. Okay, so basically we have missed out on the processes by which these clouds are formed. So within this 27 kilometers the resolution that these models give us, we have missed out on many physics which is wrong. Okay. The third thing is that the time scale. Some of the clouds will have only a 15-minute or a 1-hour time scale, whereas all these models initialize only after 6. So the frequency is only once a day or twice a day or 6 hourly. So by that time the event is over. Okay. So the temporal and spatial resolutions are a limitation in all the GCMs, which doesn't allow us to actually predict the weather in a very convincing manner. So does that mean that we cannot learn anything from them? That's not true. The thing you have to do is you have to take these as a guidance, and you have to add your own dynamical aspect to these things. Okay, so you just can't believe in these weather forecasting models. You have to take this, and you have to take the synoptic scale charts that we talked about, the wind charts, the different temperature charts. Where is the temperature lower, higher? Okay, so those kind of things, if you add on to this, then you can actually have a much better handle on weather. Okay, maybe you can. Yes.
Yeah, one question. Is this the reason how the weather company and others are offering forecasting up to even a kilometer or even a 2 square kilometers sort of an area?
Yeah. Yes, they are running. They are running the regional forecasting model, which is the regional model, which you can actually go up to 1 kilometer or 2 kilometers. That's how they are offering. But the issue is that, like I said, even these RCMs, they get some of their data from the GCM. So the GCMs, if they are wrong, then the RCM will also be wrong. So that is why, even though the weather companies give 1 kilometer, 2 kilometer kind of weather forecast, the accuracy will still be not very high.
Professor Sridhar, also can you kindly comment on the role of initial conditions being wrong?
Yes, that I have that. It is there. I mean, so it is. So I'll maybe I'll talk. We'll talk about it after lunch. Yeah, it's there.
Can I ask a few questions?
Yes, please.
So, is there is there any ranking of weather models, or is there any forecast verification that happens? How does that work?
That would be very, very useful to see what they said and what actually happened. And I mean, if someone can maintain that.
Yes, so that I think they do it. So if you see, so of course I have taken this from internet, but the ECMWF, one of the claim to fame was the prediction of Hurricane Sandy for US. GFS was showing that it is not going to make landfall; it is going to curve in the ocean. But ECMWF 7 days before the hurricane was about to make landfall, it kind of accurately predicted that it is going to move towards US, towards New York. Okay, so that was the claim to fame for ECMWF. GFS could only pick it up 3 days before the event was happening. Okay. So this is kind of a check. So this is only one check, but there are multiple checks. I think Cyclone Varda is the other example, which I think a lot of people from Chennai actually, ECMWF did a better job on that. But see, so in terms of these cyclone predictions, ECMWF has a better metric. Like it is a better performing model, is what people believe. But coming to monsoon, all models are bad. So IMD GFS is better. I can vouch for it because I had so the last 2 years for during monsoon season I have been kind of following IMD GFS outputs, and it has been performing much better than ECMWF and GFS. Okay, so for monsoon, none of these models can predict things, and they can only predict after either after the event has happened or just 1 or 2 hours before the event is going to happen. Okay, the reason is again because cyclone. See, cyclone is a very unique feature. Cyclone is a very unique structure. We know a lot about cyclone, and there is a lot of initial condition which Professor Vardhan also asked. What is the role of initial condition? So there are, and cyclone is a structure which actually has a set dynamics in the sense that this is how it forms, like 27 degrees, 20 degrees and above temperature. If it is there, then cyclone can form. If the wind shear is lower, if if your what do you call moisture content is more in the ocean, and if the Pacific ridges, the Indo-China ridge and Indo-Arabian ridges are positioned. So those kind of things, we have a better understanding because those are synoptic scale features. Those are things which have resolution greater than 27 kilometers, okay, or 14 kilometers. So it is to some extent easier to predict cyclones, okay. And for cyclones, the good thing is you have time from formation to hitting. You have like 4 or 5 days, okay. But monsoon systems are not like that. Monsoon systems, you have systems, you have monsoon which are controlled by as small as 5 kilometer. So some process which is as small as 5 kilometers to as large as 100 kilometers. So the range of scales becomes very large, okay. And that is why monsoon prediction is very difficult, and that is why for a country like us, so whatever you use, we use GCM, you use RCM, we are not going to get a very good handle on monsoon unless we couple this models with our dynamical understanding. So when I talk about monsoon, I will show you some features which are actually key in predicting the monsoon cloud movement. Okay, so that is where the aspect of dynamics comes into picture, or I would say experience, like so rather than just depending on the models, what do you look for? Like what is the extra thing that you know that you can add that knowledge so that you can improve the predictive capability. I hope I'm making some sense here.
Yeah, thank you.
So there is no, so a short answer to your question is there is no ranking as such. But yeah, for cyclones, maybe there is, this is better, probably ECMWF is better. But when it comes to monsoon, then it's just a toss of a coin. Like one day GFS might be right, one day ECMWF might be right, one day ICON might be right. You never know.
Okay, thank you.
Sir?
Yes.
Sir, you told about that global, 1 minute, sir. You told about the greenhouse effect, no, sir. It limit 160 amount of heat towards the earth, no, sir.
Yeah.
So if the greenhouse gases are increasing, will it increase to 170, 180? Is it possible, sir? That heat amount?
Yeah, that is just a number. That was just an example. It can change. I mean, that is just a number that I gave. It's a random number. So yeah, it can reach higher levels. It's very possible, depending on the chemical reactions that are happening between the gases.
No, sir. They're telling about global warming, no, sir. Well, actually, those numbers are increasing, sir. Or it has nothing with the numbers, sir. Can you please explain about that, sir?
Say that again. I didn't get that. Sorry.
What, sir?
Can you repeat it? I didn't understand the last part. What?
So for actually global warming, many are telling, no, sir. Global warming means the temperature of the atmosphere is increasing, no, sir. I'm correct only, no, sir. So does it have anything with that number, sir? So if the number increases, global warming is happening like that. Anything is there, sir?
No, so that that number again is just unit. So global warming it is looked at from a completely different viewpoint. Whether how much amount of so it's mostly looked at from the temperature of the ocean and temperature of the atmosphere. So if the temperature of the ocean is increasing steadily, then that means warming is happening. And we are seeing in terms of even the surface heating, we are seeing every year is a warmer year. Like starting from 2018 was the warmest year, 2019 now is the warmest year, now 2020 is the warmest year. I mean, so every year is becoming a warmer year, year by year. So that number is not very easy to measure because it is you cannot measure it. You can just get an estimate for that number.
So if the carbon dioxide is increasing, then more heat will be emitted. No, sir.
Correct. Yes.
And you told about the resolution, no, sir. What is resolution, sir? Is it like size of one cell like that, sir?
Yes. It is how much you can resolve in that one box.
Okay, sir. Then what is step, sir? Step you told about this many hours.
How many time scale? So the output. So once the output is there, how many time steps it is available? Is the forecast available for every 1 hour or every 3 hours or every 6 hours? That is the step that I'm talking about. So you can get a forecast for every 1 hour or every 2 hours or every 6 hours. That is the steps.
Right. Sir, I have got a question. This is Makran. Okay. So typically for kind of a amateur observer like myself, and I'm sure there'll be a lot of people around like me, what would you really recommend so that okay, let me just reframe the question. So what steps actually you would really advise us to kind of have a reasonable understanding of, say, weather maybe in, say, maybe next 24 to 36 hours, a kind of broad steps.
Okay, so that is the kind of the conclusion. So tomorrow afternoon, I think when we'll be doing some. So you will have a laptop with you, of course. So we will go to websites and we will kind of have this step-by-step thing where at least I will share what I look for or what I do, and that is probably a good way to start. So there are so the thing is that it's not. So many people just look at windy.com and because it's very easy, right? I mean, if you go to windy.com, you just click on rain and it will tell you how much rain is going to get accumulated for the next 10 days. So it's a very easy thing, but 95% of the time it's wrong. Okay. The quantum of rain is always is wrong. So what are the other additional things that you can check so that you don't believe them, but you question the models? Like, why is the model telling this, whereas so one simple thing is the sea surface temperature is not high, and why is the model showing a convection at this thing? So then you start getting into the question of whether there is a wave activity. So there are 5 things which are important. So one is the convection from the so one is the temperature, the sea surface temperature of the ocean, the temperature of the ocean. The second is MJO, the Madden oscillation, how it moves around the globe. The third thing is your waves. How is the Rossby and Kelvin waves behaving? Okay, and then there are many other things which we will discuss. But these 4 things are some things. If you kind of start questioning the models, then you will have over a month or two, you'll actually develop a reasonable strength of forecasting, which you can tweet and which you can actually kind of start tweeting or sharing it with your friends and all these people. Of course, it is sometimes it will be wrong, but
also there are these things called model skill scores or something. Skill score for the model that says how accurate the model was. I think these are. Over a period of time, they update what the model predicted and what actually happened. But I think we can learn more by documenting this ourselves.
No. Yeah, of course, correct. You can learn by documenting it ourselves, correct. So and you can do a better job because you are not looking at only the model, but you're also looking at other aspects of what happened, and that is the next thing that is coming in weather, which is machine learning. So people are actually documenting this machine learning and or AI. People are actually documenting this. What was the wind pattern? What was the temperature? What was the pressure? What was the humidity? Let's say these things, and what was the output by the model, and whether it was right or wrong. And then they do a mining, as in if these things come together, then it is giving rain. If these things don't come together, then it is not giving rain. So those kind of documentation is what is the next step, which is kind of AI or ML, and the algorithms are actually based on these things. So looking for patterns and trying to see whether the patterns that you saw, are they matching with the what happened. So that is exactly what is the pattern matching that I'm talking about. And the pattern matching comes only if you don't believe in models too much. If you start questioning the models, then only the patterns will come. Like, because for instance, I don't know how many people here know about Rossby waves or Kelvin waves, or how to look at the Rossby waves, whether it is coming or not, and what happened during cyclone Amphan, for instance, where a Kelvin wave came and it actually gave the boost for it to become a super cyclone. So those are the kind of things that I think we need to embrace and use model as a guidance, because of course models are very useful because you get the futuristic wind and pressure from those models. But at the same time, I think it's important for us to link whatever data you have with what the model is doing. So that is where the gap, which is the dynamics and statistics, will connect that gap to some extent. Okay, so maybe we'll. I think it's almost 1:10, and we will break for 1 hour and come back at 2:10, and then maybe start talking about some of the processes. What is a front? What is so those kind of things, so that we get a better idea on what are the patterns that we are looking for. So this is where exactly I want to switch gears, where we talk about the patterns. What patterns should we be seeing, and why is that useful for us? Okay.
Sir, in my area we had power cuts, sir. Sorry, sir. I could not hear what you told at that time, sir.
Okay, I will
Yes,
tell you later. Okay, because
yes,
I think
sir.
right now we'll end the session and then we will.
Okay, sir. Okay, sir. Thank you, sir.
Thank you so much, and we'll meet around 2:10 or 2:15 as and when you guys are ready. No problem.
Okay, thank you, sir.
So
Thank you,
should we log off and log in, Professor? Sorry, is it?
Yeah, you can log off and log in, not a problem.
Cool. Thank you.
Yeah, you can log off and same link, using the same link, just log in whenever you're ready. After 2:10 is when I'm thinking I'll log.